and we are going to talk about specific kinds of circuits and how some are different from others. It turns out that we can have two different kinds of circuits with resistors in them. The first kind is the easiest kind to kind of wrap your brain around, and it is called a series circuit. When you have resistors in series, there is a single path from the battery through each circuit, through each element, or resistor or light bulb or whatever, and then back to the battery. So that means it's one loop, one circle. So we go from the battery up through resistor 1, resistor 2, resistor 3, and back. There's a single loop. The current through each resistor when they are in series like this is the same. And that makes sense, right? The amount of electrons that leave this terminal has to be the same amount that comes in. So all of them flow through each of these resistors. So that means current is the same. But the voltage over each resistor, or the potential difference between here and here, and then here and here, and then here and here, depends on how strong that resistor is. And it turns out we can figure out how much voltage is used over each of those resistors by looking at the total. The total voltage of the whole thing has to be equal to the voltage of each resistor added together. And resistance, we can figure out by finding something called equivalent resistance. Equivalent resistance is what resistance we would need to take all three of those resistors out and replace them with one. So let's do an example. If I have two resistors here in series, this one has 2 ohms and this one has 3 ohms. If I wanted to take those out and replace them with one resistor with the same resistance, this would have to be 2 plus 3, which is 5. This right here is the equivalent resistance, or REQ. And the more resistors you have, the more numbers you have to add together to get the equivalent resistance. When the resistors are in series, all in one loop together, it's really easy to find equivalent resistance. All you have to do is add them together. Now, why would we put resistors in series in a circuit? Well, they're very cheap and easy to make. You don't need a whole lot of wire. It's not complicated. And you have very low current and power draw from your voltage source. This is a really good thing because it's not the potential or the voltage that will hurt somebody if they get shocked. It's the current. It's how many electrons are running through that person in a given time. So the lower the current can be, the safer it is. The disadvantages of this is that if one thing fails, the whole circuit goes kaput. So I don't know if you guys are actually old enough to remember this, but Christmas lights used to be wired in series. If you had one Christmas light go out on your whole strand, the whole string didn't work. And you would have to go through and replace each of the bulbs in that strand to figure out which one broke. It was a pain in the butt. So now they are not wired in series. And the second disadvantage is that the components have to share the voltage. Nothing gets full power. So if we have 2 light bulbs and they're hooked up in series, each of those is only going to get a portion of the total voltage from the battery. So they might not be very bright. To summarize all of the important math things for series circuits, and this is really important, you probably want to write down exactly what I put on this slide because it will help you a lot with the math later on. The equivalent resistance for a circuit with resistors in series is just the sum of the individuals. running through your circuit is going to be the same amount of current through each resistor. They each get the same. Oh, I wrote the 3 here. And these should not be plus signs, these should be equal signs. They are all the same. So if my battery puts out a current of 2 amps, every single resistor has a current of 2 amps. They are all equal. And finally, the total voltage in your circuit can be found by adding the individual voltages across each resistor. Apparently, it's very hard to write and talk at the same time, at least for me. So for series circuits, Req equals R1 plus R2 plus R3 plus R4 plus blah, blah, blah. Same kind of rule for voltage. Total voltage equals V1 plus V2 plus V3 plus V4 plus blah, blah, blah. And I total equals I1 equals I2 equals I3, and so on and so forth. So now, how would we use this information in a problem? Well, I have a fairly difficult problem that we are going to walk through together that requires you to solve for the voltage, resistance, and current for pretty much every single aspect of this circuit. So our circuit diagram is right here. We have one battery and 3 resistors, and they're all in the same loop, so we know this is a series circuit. So let's read the problem. 3 resistors are connected in series. If placed in a circuit with a 12-volt power supply, determine the equivalent resistance, the total circuit current, and the voltage drop across and current at each resistor. So we want to find equivalent resistance. If we were to replace these 3 resistors with just one, how much resistance would it have to have? Find the total current. How much current is running through this entire circuit? Find how much current is running through each individual resistor. So I1 means how much current is passing through the first resistor. The numbers represent which resistor we're talking about. And finally, find the voltage drop over each resistor. So how much voltage is lost over each individual one. Now, I have a few rules that we can follow when solving a problem like this that will hopefully help. When you're solving a circuit diagram, the first thing you want to do is solve for equivalent resistance. Once you're done with that, you need to figure out what stays unchanged. And what I mean by that is in a series circuit, there is something that does not change when it goes across the resistors. It is the same for all of them. So you need to go back to your notes and figure out which thing that is. And that will help you answer some of the problems. And finally, we want to use Ohm's law to solve for whatever's left. And just a little reminder about Ohm's law. It's that voltage equals current times resistance. So let's go ahead and see if we can follow these 3 steps to solve for everything that we need to here. Step number 1 is find equivalent resistance. So Req. If we go back to our rules here, we see that Req for a series circuit is R1 plus R2 plus R3. So R1, it may be kind of hard for you to see, but I'll tell you what the numbers are. R1 up here is equal to 11 ohms. R2, which is the next one, is equal to 7 ohms, and we add them together. That's the rule for series circuits. And R3 is 20 ohms. And when we add all of those together, we find that the equivalent resistance in this circuit is equal to 38 ohms. So we've got that one done. 38. Now, step number 2. So we've done step number 1 here. Step 2 is figure out what stays unchanged. Well, let's look at our rules here. Which one of these has only equal signs in it? Well, that would be the current. In a series circuit, the total current has to be equal to the current through each resistor. So we can use this information to our advantage. We know I call current blue, that the total current equals the current through 1, which is equal to the current through resistor 2, which is equal to the current through resistor 3. And how are we going to solve this? Well, we use Ohm's law. So, to solve for this one, the total current, we know V equals IR. We know that the total voltage for this circuit is 12 volts, and that's equal to the total current times the equivalent resistance, or how much resistance this thing has in it total, and that's 38 ohms. So we know that the total current is equal to 0.32 ohms. All I did was I took 12 and divided by 38. So we have total current done. But it turns out we know that the total current is the same as the current running through each individual resistor. So this is also equal to I1, which is equal to I2, which is equal to I3. All of these, the current through each individual resistor is the same as the total current, which is 0.32. They are all exactly the same. So now we have solved for most of our little boxes up here. We've solved for equivalent resistance. We've solved for total current. We've solved for current through resistor 1, resistor 2, and resistor 3. The final step, if we go back to our little checklist, is to use Ohm's law. So we did this one. That was green and blue. Use Ohm's law to solve for whatever is left over. So we know the one thing we have to figure out now is the voltage drop across each one. That is what these three boxes are left. So Ohm's law tells us that V equals IR. So we can use this equation for each of the three different resistors. So the voltage across resistor 1 is going to be the current across resistor 1, which is 0.32 because it's the same for all of them, times the resistance of resistor 1, which in this case is 11. And when you multiply those, you get 3.52 volts. The voltage across resistor 2 follow the same logic. Resistor 2 has a current of 0.32 because they all have the same current running through them. But resistor 2 only has a resistance of 7 ohms. So the total voltage drop across resistor 2 is 2.24 volts. And finally, the voltage across resistor 3 is the same current, 0.32, times 20 ohms. And that gives us an answer of 6.4 volts. Now, we have figured out everything. We used all three of our steps. We filled in all of these boxes. We have answers all over the place. So let me circle them and just run through them again. We found equivalent resistance to be 38 ohms. We found total current to be 0.32, and that has to be the same as the current through each individual resistor. And we found the total voltage drop across each individual resistor. If you want to double check your work, the total voltage drop here, when you add them together, should be equal to 12. If you add 3.52 plus 2.24 plus 6.4, that does indeed give you about 12 volts. It'll be a little more than 12 because we round it up, but this double checks your work. If you add each of the individual voltages together and get something completely different from the total voltage of your circuit or the voltage of your battery, that means you made a math error somewhere. So this is a really good way to check to make sure that your math is spot on. So I know we just did a lot, but this is an example of how you would solve for unknowns in a series circuit. But that's only one kind of circuit. We have another kind of circuit out there, and it is called a parallel circuit. A parallel circuit has multiple loops. You can't put your finger or your pencil on the battery and run it all the way around through everything in one single loop. That's series. This one has more. A parallel connection splits the current, but the voltage across each loop is the same. So if this is a 12-volt battery, that means this loop has 12 volts, and this loop has 12 volts, and this loop has 12 volts. Each loop has the same amount of potential as the power source. Now the current does not. The current splits because current is a physical thing, right? It's the amount of charge running through your wire in a given time. So the charge will split itself up. And if you look at the amount of charge you have running through this loop, and then this loop, and then this loop, if you look at these individual currents and add them together, that will give you the total current. So this is total. This is current 1, current 2, and current 3. When you add 1, 2, and 3 together, you get the total. Now, the tricky thing about parallel circuits is equivalent resistance. In order to calculate equivalent resistance, you need to look at the reciprocal of the equivalent resistance. So, unlike series circuits where you just added R1, R2, and R3, you have to take 1 over R1, add that to 1 over R2, add that to 1 over R3, and that will give you 1 over your equivalent resistance. So you will need to flip that after. So let's do an example. 1 over Req equals, let's say we have 2 resistors. The first one is 3 ohms and the second one is 2 ohms. So we have 1 over 3 plus 1 over 2. Remember, when you add these together, you need to find a common denominator, or you can just use your calculator. So this is going to be equal to 2/6 plus 3/6, which is equal to 5/6. So the inverse of your equivalent resistance is 5/6. So in order to find equivalent resistance, you need to flip both of these. So your total equivalent resistance is 6/5 of an ohm. Now, why would we do this? This is just confusing. Well, it turns out that when you put things in parallel, if one component fails, the rest will continue to work. So it's like those Christmas lights I was talking about. If one of them goes out, that does not mean the whole strand goes out. That is because they're wired in parallel. And everything gets full voltage. So if you have a pretty small voltage source, but you have a lot of things that you need to power, you're going to want to put them in parallel. The disadvantages, obviously they're more complicated and they cost more to make. You need much more wire and much more material. And the other thing is they use more power and have a higher current draw. Because the current has to split over each loop, the total current running through your circuit can get pretty high, and that's kind of dangerous. So let's do a mathematical summary of parallel circuits. Equivalent resistance is found by using the reciprocal. 1 over Req equals 1 over R1 plus 1 over R2 plus 1 over R3, etc. The total current gets split up over each loop. So total current equals I1 plus I2 plus I3 plus blah, blah, blah. The voltage, however, stays the same through each loop. So the total voltage is the same as the voltage in loop 1, which is the same as loop 2, same as loop 3, and so on. So now, let's see if we can use these rules to solve a very similar problem to the series one, but about parallel circuits. So we have the same 3 resistors as we did before, an 11, a 7, and a 20. But these 3 resistors are connected in parallel. They're placed in a circuit with a 12-volt power supply. Determine the equivalent resistance, the total current through the circuit, the current through each loop, and the voltage drop through each loop. Now, I'm going to go ahead and pull our rules down so that we can look at a dual page screen, and hopefully that will help us solve this problem. Okay, so we have our problem, we have our steps, and on the other page, which I'll show you, we have our equations. So remember, the very first step you want to try and do is find equivalent resistance. So we look at our equations. The equivalent resistance of a parallel circuit is found by this equation. So we can go ahead and use that. 1 over Req is equal to 1 over R1, in this case it's 11, plus 1 over 7 plus 1 over 20. You don't want to find a common denominator for these things, you just want to plug them into your calculator. When you add 1 over 11 plus 1 over 7 plus 1 over 20, you get some number. But that number is not yet your equivalent resistance. Remember, you still need to flip whatever number you get out of this to find equivalent resistance. Once you find that number and flip it, you should find that your equivalent resistance is 3.5 ohms. I would encourage you to follow along with me here and try and do this math on your calculator as we go, pausing the video. If you don't get this number, go back and try again. You may have forgotten to flip it or may have forgotten to do 1 over a certain number. So we have step 1 done. Find Req. Cha-ching! Step 2, figure out what stays unchanged. Well, looking at our set of equations, the only thing here that has equal signs all over the place is voltage. So we know that the total voltage has to be the same as the voltage across each individual resistor. So what does that mean? Well, that means the total voltage is whatever our battery is, right? So the total voltage is 12. So if the total voltage is 12 volts, that means that each loop has to have the same amount. So loop 1 and loop 2 and loop 3 all get 12 volts. They all get the same. That's nice and easy. We can check these 3 boxes off. We automatically know they get 12 volts. So number 2 is done. Number 3 is using Ohm's law to solve for what's left. Well, we have 4 things left to solve. The total current in the system, right here, and the individual currents in each resistor, right there. You can do it in any order you want at this point. My personal preference is to do the total first, and then I'll do the other ones after. But it really doesn't matter. So let's do total current. We know Ohm's law equals V equals IR. The total voltage in this system is 12 volts. That has to be equal to the total current times the total resistance. And we already solved for equivalent resistance. It's 3.5 ohms. So when you do that out, you find that the total current in this circuit is 3.4 amps. Now let's pause. 3.4 is pretty high. In the series circuit, where we had the same resistors, the total current was only 0.32, which is much, much smaller. That is a much safer circuit. So we know the total current is 0.34 amps. So we've done that. Now we use the same steps to solve for the current through each loop. So we know that loop 1 gets 12 volts. We want to solve for the current through that loop. And we know that the resistor in that loop has 11 ohms of resistance. So if we divide both sides by 11 to solve for I, this loop has a total current of 1.1 amps. Loop number 2 still has 12 volts. They all get the same voltage. And the resistance is 7 ohms. So divide 12 by 7, we get 1.7 amps. Finally, loop 3 still gets 12 volts, but it has a resistance of 20 ohms. So 12 divided by 20 is 0.6 amps. So now we have found the current through loop 1, loop 2, and loop 3. And remember, a good way to check is that the rule for parallel circuits is that the currents add. Current through loop 1 plus loop 3 plus loop 2 is going to be your total current. So what we can do is we can double check our answers here. 1.1 plus 1.7 plus 0.6 should equal our total current for the system. And when you add them together, you find that it does indeed equal 3.4 amps. Check. So just like we did before, I'm going to do a little rundown of what we solved for. We solved for equivalent resistance, which is 3.5 ohms. We solved for the amount of voltage running through each loop, which was 12 volts. We solved for the total current running through the entire circuit, 3.4 amps. And we solved for the current running through each individual loop. So hopefully this made a little bit of sense to you. You're going to test your skills in your homework for tonight. Please follow the previous problems, the ones we just did together. Follow all of the equations and follow each of the steps for problem solving, and you should be in good shape at least to get started. So you only have one question. The series circuit at the right depicts two resistors connected to a voltage source. This voltage source is a 48 volt source, and the resistor values are 6.4 ohms and 3.9 ohms. Part A, determine the equivalent resistance of this circuit. B, determine the current in the circuit. So just tell me total current. And C, determine the voltage drop across each individual resistor. So your job is to figure out what kind of resistor this, or what kind of circuit this is, follow the rules, and answer these questions.